We are starting section 7-2 today, solving exponential equations and inequalities. We're just going to be dealing with equations today. We've talked about how to graph an exponential function, and you know what it looks like compared to a linear function. So what we're going to do today is solve exponential equations. So new vocabulary would be exponential equation, compound interest, and exponential inequalities that we're going to look at a different day. So for the first thing about the property of equality for exponential functions, and this just makes it super easy when you think about it. And here it is. If I'm reading from the example part, if 3 to the x equals 3 to the 5th power, if this is true, then that means that x equals 5. So it's like, well, duh, that kind of makes sense. So if the bases are the same, exactly the same, and the two expressions are equal to each other, then those powers have to be equal to each other. And that's the property of equality for exponential functions. So we're going to make use of that. Of course, they won't all be that easy. So here's our first example. Solve the equation 3 to the x power equals 9 to the 4th power. Now, they're not the same. Here's a 3, here's a 9. They're not the same. But remember, we can think of 9 as 3 to the 2nd power. So I'm going to rewrite that. So I have 3 to the x on the left side, and I'm going to rewrite the 9 as 3 squared. Notice I put it in parentheses. That's a good habit to have. And that whole thing, the 9 was raised to the 4th power, so my 3 squared is raised to the 4th power. And then remember from our exponent rules, if you have a power to a power, you multiply those. So I get 3 to the x power equals 3 to the 8th power, because 2 times 4 is 8. So now the bases are the same, so I can say x equals 8. Now you can always check these if you wanted to. You can grab a calculator and check 3 to the 8th power and see what you get, and then check 9 to the 4th power, and you can verify that you get the same thing. Okay, on this next one. Now the 2, we can't change this to anything, but remember we're trying to get a common base, so that's our goal. Find a common base. Okay, so I can change this 4 into a 2 squared, because then I would have a common base. So I'm not changing the left-hand side, but the right-hand side, I'm changing the 4 to a 2 squared. Whoops. Put that like this. So we have 2 squared, and then that's raised to the 2x minus 1 power. All right? So the next thing I do, power to a power, you multiply the exponents. So when you multiply the exponents, you're multiplying 2 times the whole thing. So you do have to distribute when you multiply. So I get 2 to the 5x equals 2, and then I'm going to multiply 2 times 2x is 4x. 2 times 1, and it's a minus, is 2. So don't forget to distribute. And now the bases are the same, so I can set the powers equal to each other and then just solve this equation. So I'm going to subtract 4x from both sides, and I get x equals -2. And that's my answer. Again, you can check it. If you plugged in a -2 up here, you get 2 to the -10th. You can see what that equals. You can plug in a -2 here and see what you get. And you can check it on your calculator. So here's one for you to try. So pause it and try it. So on this problem, you would have the option of changing them both, but you could also just leave this as 4 to the x and think of 64 as 4 cubed. So you would have 4 cubed to the 3rd power. So we get 4 to the x equals 4 to the 9th, so x equals 9. So you should have got this as an answer. Now, you also could have done, thought of this as 2 squared. You know what, we won't go there. It is true that you could have done it a different way with 2's, because you couldn't do it with a base of 2, but this is probably what you would think of. Okay, so go ahead and try this one. So pause it and try it. Okay, so I'm not going to do anything to the left-hand side. So I have 3 to the 2x. I'm going to change the 9 to 3 squared. So I get 3 squared raised to the 5x minus 4. Then I'm going to have 3 to the 2x equals, remember you have to distribute when you multiply the powers, so you get 10x minus 8. Once the bases are the same, you can say 2x equals 10x minus 8, and then you're going to just solve for x. So we get negative 8x equals negative 8, so x equals 1, and the answer is A. Okay, now I added in a few others of these because I want you to remember, what does it mean, how do we find a common base for one like this? So sometimes you go with your gut instinct. If you had to look at these, I've got a 5 here, I've got a 25 here, so think about, what do I think the common base is? And hopefully, I would ask you if we had class, but hopefully you think, oh wait, I think it's going to be 5. You almost kind of go with a gut instinct, and the common base would actually be 5. So over here, we're not going to change anything because it's already a 5. But we got to do something here. So I know that 5 squared is 25. So I know somehow it's going to involve a 5 squared. But I also know that this is a reciprocal. So think about what happens when you had a reciprocal. We had a negative exponent. So because it's a reciprocal, it's 5 to the negative 2. Because remember what a negative exponent means. The negative tells you to flip it, but then the squared tells you to square it. So you square the 5, but then you flip it. So this is going to be 5 to the negative 2. So that's a little tricky, and you are going to have to remember that with negative exponents, it means reciprocal. Now the bases are the same, so we could say 2x plus 1 equals negative 2, and you solve for x. So x equals negative 3/2, and that's okay to have a fraction, and I would just leave it like that. Okay, so a little trickier on those. So here's another one. Again, go for a gut instinct. Now you might look at this and say, when you're thinking of a common base, your first thought might be, well, maybe it's 9. But then you have to ask yourself, can I raise 9 to a power and get 27? 9 to the first power is 9. 9 squared is 81, so that wouldn't work. So then you have to think, okay, well, is there another number that that could give me a 9 and could give me a 27? So hopefully you think 3. Because we can write the 9 as 3 squared, and we can think of 27 as 3 cubed. So 3 is the common base for both of those. So I'm going to rewrite the 9 as 3 squared. Okay? And I'm going to rewrite the 27 as 3 cubed, but it's reciprocal. So that means it's 3 to the negative 3. So remember, 3 to the negative 3 would be the reciprocal. You'd flip it over, so you'd have 1 over 27. So then you're going to distribute the power. So we have 3 to the 4x minus 10 equals 3 to the negative 3. And then once you have a common base, then you can set the powers equal to each other and solve for x. So you add 10 and you get 7. So we get x equals 7/4. And again, it's okay to get answers like that. All right, so on this one I had to change them both. I had to change the 9, I had to think of that as 3 squared, the 27 is 3 cubed, but then it was a reciprocal, so a negative exponent. A little tricky. Okay, this is different now, and we've done something like this before. Write an exponential equation that passes through the points, and we have this information. Actually, this one is a little different than what we've done before because it's not necessarily the exponential growth or decay. It's not going to involve the 1 plus r. It's not the same formula. But do recall that for an exponential equation, our general format is y equals a times b to the x. And also remember that this value of a was the y-intercept. Well, notice that this is the y-intercept. How do you know that? Because the x-coordinate is 0. So basically, we're told that this is the value of a that gets plugged into my equation. So I'm going to have y equals 1,487 times b to the x power. This is the equation. Well, that's too many variables. I don't know what b is, but they give me a value, they give me an additional point, which means if I plug in a 5 for x and a 275 for y, because this has to make the equation true, I'll be able to solve for b, and that's what we actually have to do. So I'm going to plug in the 275 for the y. I have 1,487 times 5 to the x power. And I have to solve, oops, wait, back up. That was backwards. B to the 5th power, how's that? Okay, so we're plugging in the 5 for the x. So then we have to solve this. So I'm going to divide, I need to get the b by itself. So I'm going to divide by 1,487. Let me find my calculator. Okay, so I divided that. So I get approximately 0.1849 equals b to the 5th power. So now I need to undo raising something to the 5th power. So think about how you're going to undo raising to the 5th power. Well, you have to take the 5th root. And to take the 5th root, we're going to have to use our calculators here. If you click on Math and you go down to number 5, you'll see this one here. I need to put a 5 there, so you just kind of go back. And if I want to do a non-rounded, if you do 0.1849, that's okay. But if you go second and then the negative key, which above there it's ANS, that's going to recall what the last thing it did. So it's going to recall that stored answer. The advantage of this is now when I round for B, and I get that B is approximately 0.7135, I didn't round twice, because if I rounded here 0.1849 and then I did that and then I rounded again, the more you round, you're not as accurate in math. So you really only want to round one time at the end of your problem. So I did that, so this would be a good answer. Now, I'm not done yet, because notice that the question says write an exponential equation. So, my work's all done, but I have to put that together. So we have y equals, remember the value of a was 1,487 times 0.7135 raised to the x power. This would be my solution. Now I have a question for you. Is this growth or decay? So take a minute to think about that. Does this represent growth or decay? And I'll tell you where to look at. It's all about this number right here. That tells us if it's growth or decay. Notice that this number is less than 1. And because that this number is less than 1, this is decay. If you looked at this graph on your graphing calculator, you're going to find that it's going to have this kind of shape to it. It's because it's decay. So it will have that general shape. Okay, so here's a problem where we're going to use that idea. In the year 2000, the population of Phoenix was 1,321,045. By 2007, it was estimated at 1,512,986. Write an exponential function that could be used to model the population of Phoenix. Write x in terms of the number of years since 2000. So this is really key right here. Because this is basically telling us that for our first number, in the year 2000, there have been 0 years since 2000. So that's x is 0. And we have 1,321,045. So that's our first ordered pair. And then 2007 is 7 years later. So 7 years later, it was 1,512,986. So now it's exactly the same problem that we just did. This is my value of a. My equation, y equals a times b to the x. So I start filling things in. So I have this number times b to the x, and then remember I have to solve for b. Here's my x value, here's my y value. Okay, so then we're going to divide by this number. Aren't you glad you have a calculator? So we have so here we get 1.1453, if I go 4 decimal places, equals b to the x. Oh, oops. I know you're probably saying, you forgot to put the 7, you forgot to put the 7. I didn't hear you. So now we have to take the 7th root. So here's another trick. If you put the 7 in first, and then you go to the math, and I'm going to hit number 5, it knew then to put the 7 there. And I'm going to do the 7th root. So I get that b is about 1.02. It'd be a 0 there. We'll leave it like that. Actually, because with exponential functions, you really should round a little bit more, have a little more accuracy. So I'm going to go 0.196. So then my equation is y equals 1,321,045 times 1.0196 to the x power. Put some commas in there. This is my mathematical model that I could use. And notice here, this is bigger than 1, so this actually would show growth. So same exact type of problem as, even though it had word problem, as we just did, where you have the y-intercept, you fill in the other point for x and y, and then you'll be able to solve for b. Okay, so here we're asked to make a prediction for 2013, which is kind of funny because, obviously it's way past 2013. So you're going to use the model you just created. And remember what x represents. X represents the number of years since 2000. So we want to know when x equals 13, because that would be that many years after 2000. So I'm just going to substitute in a 13. So I'm going to recopy. I've been recopying this number a lot. And I am going to use the rounded answer this time. We have 1321045 times 1.0196 raised to the 13th power. And my answer I get for the predicted population, and we'll just round to the nearest person, would be about 1,700,221. Okay, we are going to end there. And so you are going to be uploading your notes from watching the video, and then tomorrow you will have an assignment similar to these problems. So you want to make sure that, if you need to go back and look at any parts of this video again, or you might need to look in your textbook at some of the examples, or remember you also have those personal tutor videos in your electronic textbook that you could use if you need to.